Today's lesson is on something called the power rule for derivatives. So taking the derivative of something that is some x to a power. So you're going to use the calculator to come up with a hypothesis on what that might be. So first we're going to graph x squared plus 1 in the calculator. So you go to your y equals, you put in x squared plus 1. I'm going to graph this on a standard window. And there is our graph of our program. Transferring this to our graph, we have a intercept at 1, and then it's 1 in each direction, and then over to a 4. There is that. Now we're going to graph the derivative. So in here, we're going to go to alpha f2 to get our numerical derivative. X alpha f4 gives me our y variables. And then when x equals x, then we're going to hit graph. And we appear to be getting a line. So my description is a line. What kind of line? So if I trace, it's going through the 0, 0. So it's some mx with a b of 0. So if I trace to, say, 1, I get a y value of 2. So if I have a line that's at 0, 0, then 1 is at 2. Okay, what is the equation of that line? Y equals 2x. Next, we'll do y equals x cubed plus 1. We'll put this in the calculator. I'm going to turn this one off for right now, and I'm going to change this to a 3 and graph. We get our nice cubic function moved up 1. So we'll transfer that to the notes. Now we want to look at the derivative. Okay. So the red one is our derivative. Okay. So it looks like a parabola. Okay, so our derivative is going to be some sort of parabola. So I'm going to leave a space here, and I'm going to say x squared. Maybe it's x squared, maybe it's some coefficient larger. So if I go to my graph and I trace, make sure you're tracing the derivative. Let's trace to 1. At 1, I get 3. Well, just normal y equals x squared at 1 would be at 1. So this one is going to be 3x squared. And we'll transfer the graph here. So 0, 0, 1 is at 3, negative 1 is at 3. And there's our derivative. Let's repeat this with x to the 4th. I'm going to change this to x to the 4th plus 1. I'm going to turn this one off. So I'm going to graph this. We get something kind of flattens out there, but there's our quartic. Now let's take a look at our derivative. Re-highlight this, so we're graphing both of them. Okay, so what does this one look like? Well, this one looks like a cubic function. So we're saying f prime of x is equal to something x cubed. So let's trace our derivative at 1. 1 is at 4. A normal x cubed at 1 would be at 1. So we're saying this is 4x cubed. 0, 1 is at 4. If you trace here, you're going to get negative 4. Okay, so maybe you're starting to see a pattern. Let's see if it holds up for x to the fifth. Okay, x to the fifth. Our graph is going to look, it'll kind of look like a cubic function, but levels off there. It's going to go, kind of goes up here, levels off. Okay, its derivative kind of looks like a parabola, but it's a little bit flat here to be a parabola. And kind of based on the pattern we've already seen, where x squared became 2x, x cubed became 3x squared, x to the fourth became 4x cubed. I'm going to go ahead and say this is going to be a quartic, where f prime of x is going to be something x to the fourth. And if we trace our derivative at 1, we get 5. And you might have been able to predict that. Okay, so looking at our pattern here, the power, x squared, x cubed, x to the fourth, x to the fifth, is now in front. And then this is 1 less than that power. The plus 1, if you think about this, this is the graph of the slope. So whether I have it centered at the origin or I move it up 1, the slopes are still going to be the same. So let's fill in this table down here with what we think they might be. So we're going to drop the power down. So this would be 2x. We've already done that one. This one is 3x squared. Here we have 4x cubed. Bring the power down, 5x, and subtract 1. 6 would be 6x to the fifth. X. Okay, this would be x to the first, right? So if I multiplied that down, I'd have 1x to the 0 if I subtracted 1. So this is just going to be 1. And if you think about this is y equals x, the slope would be 1 there. C is a constant. Okay, if I take the derivative of a constant, it's always going to be 0, because if it's a horizontal line, the slope is 0. What about x to the 100th? It would be 100x, and then my power would be 99. So how do we generalize that? We bring the power down and subtract 1 from the power. So this is the power rule. Okay, so now we're going to go back to our definition of a derivative, our limit definition of a derivative. We've come up with something, but now we need to prove it. Okay, so remember that the definition of a derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. So this is what we're going to use to find the derivatives of various powers and confirm what we saw graphically. Okay, so first we're going to do the constant. We've already talked about this graphically. If this is a horizontal line, the slope's going to be 0, but we can prove it using our limit definition. So the limit as h goes to 0 of f of x plus h. Well, if I plug in x plus h here, I'm going to get c minus f of x, which is c over h, which is just 0 over h, which is just 0. So on a note card, I'm going to put on one side c prime, on the other side is 0. The derivative of any constant is 0. Okay, so let's repeat this again with x. Again, we've already talked about this graphically, but let's confirm using our definition. Okay, so the limit as x goes to 0 of f of x plus h. So f of x plus h is just going to be x plus h. f of x is just x. Okay, well this ends up being the limit as h goes to 0. The x's cancel, so we have h over h. Working sideways here. The limit as h goes to 0 of 1 is 1. Okay, x squared. H goes to 0. F of x plus h is going to be x plus h squared minus x squared over h. So that limit keeps going until we're done. So we expand this, FOIL that, so we get x squared plus 2xh plus h squared minus x squared over h. So the x squareds cancel. So we have 2xh plus h squared over h. So we can divide out the h's to get 2x plus h. So as h goes to 0, that goes to 0, and we're left with 2x, okay, which matches what we saw. All right, so how is this working? How is this rule playing out? We're going to do one more. So we're going to have x plus h cubed minus x cubed over h. Well, how do we expand a cubic? Remember that we use this is a binomial theorem. Okay, remember we use Pascal's triangle, so 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 6, 4, 1, generated by adding the rows above it. So we take the coefficients from here, we do the first thing in descending powers and the second thing in ascending powers. So this is going to be 1x cubed plus 3x squared h plus 3xh squared plus h cubed. Okay, that's this expanded minus x cubed over h. This drops out, and hopefully you've seen that has happened every time. So we can predict that will continue to happen every time. This leaves me with the limit as h goes to 0 of 3x squared h plus 3xh squared plus h cubed over h. Sorry. Okay, so the h's are going to reduce. So we're going to have a 3x squared, a 3xh, and an h squared. Okay, the only thing that doesn't have an h is that first term, where it was the second term. So as we go to 0, this is now going to be, this goes away, just 3x squared. Okay, so the power rule works because of the binomial theorem. When we expand a polynomial, this is always going to cancel. So you're always left with the second term in that binomial expansion, which from the Pascal's triangle, the leading coefficient is going to be whatever the power is. And the power is going to be 1 less, because in the binomial expansion, this will have the same power. The second one's always going to have 1 less. So that's how the power rule works and why it works. All right, so let's put this on a note card. On one side, you want x to the n prime. On the other side, n x to the n minus 1. Okay, if we have a constant times a function, the derivative is just going to be c times f prime of x. The constant will just go along. So here, 30 times x to the fifth is going to be 30 times the derivative of x to the fifth, which is 5x to the fourth. So this is 150 x to the fourth. Okay, if we have multiple parts, f of x plus g of x prime is simply just going to be f prime of x plus g prime of x. So here, we'd multiply 4 times 2x, so that'll be 8x. Derivative of 5x is just 5. Derivative of negative 2 is 0. Okay, what about 3x minus 2 cubed? So what we're actually going to have to do is expand it first, then we can apply the power rule. Because right now we've got a function inside of a function, which we will talk about later. So I'm going to expand this using binomial theorem again. So we'll have 3x cubed plus 3x squared times negative 2 plus 3x to the first times negative 2 squared plus negative 2 cubed. So we have the first thing, I forgot my 3's, 3. So the coefficients are 1, 3, 3, 1. The powers are the first thing in descending, so 3, 2, 1, and none. The second thing in ascending, so none, 1, 2, 3. Okay, when we simplify this, we're going to have 27x cubed. This will be a negative. It's going to be 9 times 2 times 3, which is 54. We're going to have 3 times 3 times a positive 2. And then negative 2 cubed is negative 8. So now we can take this derivative. So 3x minus 2 cubed, that derivative, we're going to multiply. So 3 times 27 is 81. Subtract 1 power. Multiply negative 54 by 2 is 108. X to the first power plus 36. All right, so back to our definition of a derivative. So finding the derivative of the square root of x. Again, it's all about justifying why this works. So the limit as h goes to 0 of f of x plus h minus f of x over h. For this function is going to be the square root of x plus h minus the square root of x over h. So where do we go from here? We want to multiply, when we're dealing with radicals, the conjugate is our best friend. So I'm going to multiply this whole thing by the square root of x plus h plus the square root of x. Okay, why is that helpful? Well, when I FOIL this, this times itself is just x plus h. The middle terms, when I multiply that and that, will cancel. So then we're left with negative x over h times, we're just going to leave this alone, x plus h plus the square root of x. Okay, the x's cancel here. Okay, and now I have an h to 0. On the top, I just have h. On the bottom, I have h times the square root of x plus h plus the square root of x. Okay, and it just works. Go over here. Okay, the h on the top and the bottom cancel, so that's going to be 1 over the square root of x plus h plus the square root of x. As h goes to 0, that's going to become 0. Everything else is going to stay there. So we're evaluating the limit. So this is going to be 1 over the square root of x plus the square root of x, which is 1 over 2 root x. So from the definition of a derivative, using limits and conjugates, that's what we get. Now let's do it with the power rule. Why? How can we use the power rule? Well, x square root of x is equal to x to the 1/2. So if I apply the power rule to x to the 1/2, I'm going to multiply this power down. So that would be 1/2 x, and then subtract 1. 1/2 minus 1 is going to be a negative 1/2. Okay, well, those don't look the same, so let's do more. This is going to be the same as 1/2 times 1 over x to the 1/2. Well, x to the 1/2 is just the same as the square root of x. So 1/2 times 1 over root x is 1 over 2 root x. So let's put that on a note card. Square root of x prime is 1 over 2 root x. Okay, well, what about negative exponents? So let's do 1 over x using the definition, and then we're going to verify that with the power rule. So the limit as h goes to 0 of f of x plus h minus f of x over h for this particular equation is 1 over x plus h minus 1 over x all over h. Okay, so I'm going to get a common denominator. So I'm going to multiply this by x over x and multiply this by x plus h over x plus h. So this is going to be x over x times x plus h minus x plus h over x times x plus h all over h. So if I combine these, we're going to have x minus x. So we just have a negative h. So limit as h goes to 0. We're going to have a negative h over an x squared plus xh. Then I'm going to multiply that, rather than dividing by h, by 1 over h. Okay, so this h will actually reduce with this h. So this leaves me with the limit as h goes to 0 of a negative 1 over x squared plus xh. Well, as h goes to 0, this goes to 0, but everything else stays there. So negative 1 over x squared. Okay, getting there with our limits, getting common denominator, using the definition of a derivative. Now let's verify with the power rule, because 1 over x is the same as x to the negative 1. Well, if I apply the power rule, we'll multiply the power down, so negative 1 x, if I subtract 1 to the negative 2. Well, that's going to be the same as negative 1 over x squared. So 1 over x prime is equal to negative 1 over x squared. Okay, so we can always arrive at these using the power rule, but these are such commonly used ones that you should really get these memorized. Okay, so the difference between a vertical tangent and a cusp. If I were to graph both of these, and you can certainly graph these on your calculator. Okay, x to the 1/3 is going to look something like this. X to the 2/3 is going to look something like this. So this one has a vertical tangent here. This one has a cusp here, which we have said means we don't have a derivative. So how does that look like in the equation? Okay, so these are both powers. Okay, if f of x is x to the 1/3, I'm going to multiply down the power, x, and subtract 1. 1/3 minus 1 is a negative 2/3. Well, that's the same as 1 over 3x to the 2/3. Okay, if I try to plug in 0 here, this is undefined. So the derivative is numerically undefined at 0, graphically, because we have a vertical tangent. Okay, g prime is going to be 2/3 x. If I subtract 1 from 2/3, we get negative 1/3, which is 2 over 3x to the 1/3. Okay, if I try to plug in 0, I'm going to get undefined graphically because there's a cusp. Okay, 11, if f of x equals x, then f prime of 5 is, well, f prime of x is going to be 1. So f prime of any number I plug in there is going to be 1. Okay. So let's let f of x equal 2x to the 5th minus 3x squared. So I multiply this down, so 10x to the 4th minus 6x. The slope is going to be 10 times 1 to the 4th minus 6 times 1, which is going to be 4. And then the tangent line and the normal line. So the tangent line is going to be y, my y coordinate's negative 1, so plus 1 equals 4x minus 1. Normal line, y plus 1 equals negative 1/4 x minus 1. And then you could graph all three on your calculator. Okay, now this does evaluate each limit. You no longer have to evaluate this limit using all the algebra that we've been doing. Okay, the definition of a derivative at a value, notice there's no x's here, is the limit as h goes to 0 of f of a plus h minus f of a. So we can kind of break this down. What is f of x and what is the a that we're plugging in here? Well, hopefully you see we've got 3 times 4 plus h squared minus 3 times 4 squared. So my function is going to be 4x squared. The derivative then is 8x. And where am I evaluating this? At 4. So f prime of 4 is going to be, sorry, this should be 3x squared, 6x. So this is going to be 3x squared because we have 3 something squared. So 6x. So 6 times 4 is 24. Here, our a is going to be 9. The function is just the square root of x. So f prime of x is 1 over 2 root x from our previous example. So f prime of 9 is going to be 1 over 2 root 9, which will be 1/6. So you do need to be able to recognize that this is asking for a derivative. This is the definition of a derivative with the specific information. So that is the power rule.